We are live. So today I'm going to talk about zeros. So imagine we have a transfer function, g is equal to k, and then we have a factor numerator polynomial and a factor denominator polynomial where the z's are our zeros, the p's are our poles, and as before, here we have n poles and m zeros. And if you recall that the number of poles has to be at least as big as the number of zeros. So any physical system, which we call proper transfer function, satisfies this inequality that n is bigger than or greater than or equal to m. So just again, a summary, the p of I in this transfer function, these are the poles. And these tell us about the stability of the system. So again, the real part of the poles tell us whether the system is stable or unstable. And the imaginary part of the poles tells us whether there are oscillations in the response. And now the z of I are our zeros. And zeros tell us whether we have, or they can potentially generate overshoot or an inverse response. And so to explain these two concepts, I'm going to go through a series of examples of increasing complexity. And that'll kind of illustrate the key ideas of overshoot and inverse response. So let's start with a first order system. So this is also known as a lead lag system. So here we have g is equal to k, tau 1s plus 1 divided by tau 2s plus 1. So this system has one pole and one zero. So again, our pole is minus 1 over tau 2. And here we get this from just solving the equation tau 2 s plus 1 is equal to 0. And likewise, we have 1, 0, which is minus 1 over tau 1. And then again, that's obtained by solving the numerator polynomial, which is tau 1 s plus 1 equal to 0. Now, whenever we have a system, in particular where the order of the numerator is equal to the order of the denominator, we have to worry about a non-zero initial condition. And so we can use the initial value theorem. So the initial value theorem says that y at time equals 0 is equal to our transfer function evaluated s equals infinity. Again, this is for a unit step response. And in this case, we're going to get k tau 1 divided by tau 2. So we're going to have a non-zero initial condition. And likewise, the final value theorem tells us that y at time equals infinity is equal to g set at s equals to 0. So if we set the s's up here equal to 0, we just simply get k back. And now if we want to look at the unit step response for the system, again, so we have our final value, which is k, and our initial value, which is k tau 1 divided by tau 2. And since it's a first order system, we're going to have a first order response, but we're going to have a non-zero initial condition, right? So this is our initial value, so it's not equal to 0. But then we're going to go back to our final value, which is equal to k. And because it's a first order system, we also know that at time equals to our time constant of the system, so tau 2. So if I slide back here, again, this is our tau 2 in the denominator. Then we know that at time equals tau 2, we'll get 2/3 towards the steady state. So in this case, it's 2/3 from this initial position to this position right here. So it's 2/3 this value right here. So the distance between the initial condition and the final condition. It's important to note that with this 0, so the key thing about this 0 is it causes this jump in the initial condition. So we have this immediate jump in the response, and then we have kind of our first order response. Is that prior at t less than 0, of course, the response is assumed to be 0. And so if you were going to look at the response in the system here with time, so we have some value of y, right, our initial steady state value. Then at time equals 0, we're going to have this initial jump. This little dot right here is emphasizing the jump. And then we're going to have our first order response. So in this case, in a lead lag system, we get the lead element, which is the case of the 0, and that causes the jump in the response. And so that's an example of a 0 with a first order system or a lead lag system. The next example we're going to do is a second order system. So here we're going to have g is equal to k, tau 1 s plus 1 divided by tau 2 s plus 1, tau 3 s plus 1. So it's second order because we have a second order polynomial in the denominator. And now we have 1, 0 in the numerator. So our poles, again, for this system is minus 1 over tau 2 and minus 1 over tau 3. So we have two poles. And then we have a single zero, which is minus 1 all over tau 1. And we're going to assume, just for simplicity, that our taus are all positive. So what this means is that we have stable poles and also stable zeros. And so, yeah, stable poles and stable zeros. So stable poles means we're going to converge to a steady state. And a stable zero means we're not going to have inverse response, which I'll explain in a second. So if I'm going to sketch the response for the system, the key thing is that with a second order system, so first we can consider a second order system without a zero. So just k over tau 2s plus 1, tau 3s plus 1. And that's denoted with a dotted line. And so we're going to have the classic second order response with an inflection. The slope at time equals 0 is equal to 0. But when we have our zero in our system, what it can do is potentially lead to overshoot in the response. And by overshoot, I mean that the response is going to go past the steady state value, come up to a maximum, and then kind of converge down. So this is different than oscillations. So oscillations, we go above, below, above, below, above, below. Here we're just going above once and then kind of converging to the final steady state value. And so the key thing is that zeros accelerate the response. So by accelerating it, so here's a system without a zero, we add a zero, and basically we're shifting this curve this way, right? So we're accelerating the response. And in some cases, that zero can lead to an overshoot. So an overshoot is, again, where it kind of goes past the steady state value. So then the question becomes, when does overshoot occur? So again, let's consider the second order system with a single zero. And again, we have our gain, our two poles in the system. So overshoot occurs when tau 1 is bigger than tau 2 or tau 3. So it's bigger than tau 1 and tau 1 is bigger than tau 2 and tau 3. Or another way of saying this is that the magnitude of the zero is greater than the magnitude of all the poles. So in the case of here again, here's just as a reference point, here's a system without a zero. So that's basically equivalent to setting that tau 1 equal to 0. So if we set that equal to 0, that s disappears. And if tau 1 is bigger than tau 2 and tau 3, then we're going to get this overshoot response. However, if tau 2 is bigger than tau 1 or tau 3 is bigger than tau 1, then we're not going to get an overshoot, but we're going to get an accelerated response. So here would be the system without a zero. And then when we add the zero, first thing is, because now we have a relative degree 1 system, we don't have the inflection. But now it becomes basically like a first order response, right? And so here again, we have acceleration. Now, if that acceleration gets really big, it'll have overshoot. But in this case, we have kind of a monotonic convergence towards the steady state. So again, we can have overshoot if the zero is bigger than the poles, in which case we have the overshoot. But if the zero is not bigger than the poles, then basically we have a monotonic response that's faster than the system without the zero. So one of the kind of more interesting properties of zeros is that they can give us what's known as an inverse response. So now let's consider a transfer function g is equal to k minus tau 1 s plus 1 over tau 2 s plus 1, tau 3 s plus 1. All the taus are positive. But in this case, we have now a zero at 1 over tau 1. And because this zero is positive, it is unstable, or what we call an unstable zero. And in the case of our poles, we have minus 1 over tau 2 and minus 1 over tau 3, so we have stable response. So again, the poles tell us about stability. Zeros tell us about overshoot or an inverse response. And when you have unstable zeros, you get an inverse response. So here's an example of an inverse response. So initially we're at 0. We're going to go to our final steady state value of k, but initially we're going to go in the opposite direction and then kind of converge back to that steady state. So that's why it's called an inverse response, because the direction of the response changes as a function of time. So initially we're going down and then we're going back up. And so that's an example of an inverse response. And inverse responses can happen in certain kind of systems. Sometimes when we couple multiple feedback loops, when we talk about cascade systems, we can potentially get inverse responses, but it's just one kind of dynamic that can happen in a system. You can also get this with coupled systems, and we'll do an example later in the homework, where you'll get an inverse response like this. So to finish up, I'd just like to do some examples. So our first example is s plus 1 over 2s plus 1, s plus 3. And so in this case, what we're going to have is basically we have a 0 that's equal to minus 1, and then we have two poles at minus a half and minus 1/3. So the 0 is not bigger than the poles, right? Because minus a half is bigger than minus 1, minus a third is bigger than minus 1. And in this case, because our 0 is not bigger, we're not going to have an overshoot response. And so what we're going to get in this case is just basically what looks like a first order response. And the relative timing of this is going to be roughly equal to the biggest time constant. And so our biggest time constant is 3. So around t equals 3 will kind of give us a rough estimate of how long this response will take. Now, if we do that same system, but we have an unstable 0, so here we have minus s plus 1 over 2s plus 1, 3s plus 1. So again, our 0 here is equal to 1. And then we have a pole at minus a half and minus 1/3. So again, we're going to have a stable response, but this part, z equals 1, so the real part of the 0 is positive, so it's an unstable 0, and that tells us that we're going to have an inverse response. And again, the gain of the system is 1. And so in this case, we're going to go to a final value of 1, but we're going to have an inverse response where the system goes down and then goes back up to the final value. And again, the inverse response is due to that unstable 0. So a couple more examples. So if we have a lead-lag system, here we have our transfer function minus s plus 1 over s plus 1. Here we have a 0 at 1, so that's an unstable 0, so we're going to get an inverse response. And then we have a pole, actually that's a pole, and that's going to be minus 1. So we know it's going to be a stable response, but we could also just use basically the initial value theorem and the final value theorem to see the responses. In this case, the initial value will be minus 1 and the final value will be a 1. If I draw this up in the step response, our initial value again is minus 1, our final value is 1, so we're starting at minus 1, and then we're going to 1. At tau equals 1, which is the time constant, right, because we just have a 1 in front of the s, right? That value here is going to be kind of the 2/3 of the response, so 2/3 of the time it takes us from go minus 1 to 1. And the key thing about this system is why it is an inverse response is if we plot it up, where again we have t equals 0, we're initially at 0, right? And then we're dropping down to minus 1, so the 0 is kicking us down to minus 1, and then we're kind of coming back up to 1. So this is another example of an inverse response where we're going the opposite way. This is instantaneous. And then we kind of have the monotonic increase to the final steady state. Our last example is g over 3s plus 1, s plus 1, 2s plus 1. So in this case, our 0 is minus 1/3, and our pole is minus 1, and we also have a pole at minus 1/2. So in this case, our 0 is bigger than, so minus 1/3 is bigger than minus 1, and minus 1/3 is bigger than 1/2. And because of that, because the 0 is bigger than both of the poles, that means we're going to have an overshoot. So again, our gain is equal to 1 because we set s equal to 0. So our unit step response is going to be basically a first order kind of response, so no inflection. And then we're going to overshoot the steady state and then kind of come back to the value. And then somewhere around kind of this initial dynamic, it's going to be equal to the largest time constants around 2. So we know kind of roughly here, we can probably put that t is equal to 2. And that kind of gives us a rough estimate for the response. Whether it's here or here or here, it's kind of tough to tell without simulating the system. But that kind of gives you an idea for kind of zeros. And so with that, I'll conclude. I'll mention that my notes are posted online. So I go through kind of the math for zeros. And next week, when I post the lectures, which will probably be posted this weekend, I'm going to do practice problems for the exam. So each video, I'll try to do 2 or 3 practice problems and kind of go through the solutions for those. So once again, if you have questions or comments, please leave them in the comment section on YouTube. And let me know how you like the videos. This time I tried keeping the camera fixed and using smaller sheets of paper. Let me know if you like this better. All right, keep safe, guys. Bye.